Thanks a lot. So what a lineup in the conference. Like, I feel like I am amongst the giants in the tech industry. I feel very small. The other speakers are really legit. And this stage is so big, like it's not helping in me feeling any bigger. Like, I'm pretty sure, I'm a short guy. I'm not even sure if I'm visible from all the way back there. But as long as you can hear my voice and you can see my screen, that should be fine, right? So hi, I'm Prashant. I'm from the Netherlands, but I'm originally from Nepal. I live and work in Netherlands as a freelance front-end developer. And I'm here, it's my first time in Moscow. But I have been to Russia before in St. Petersburg, which is where I tasted the pelmeni. And I love the conference. It was because HolyJS as well. I love the conference. I love the people, the food, and all that stuff. And I'm really excited to get to know Moscow better as well. But at this very moment, I'm super excited to be standing here in front of you guys in the HolyJS stage about to give this talk. And the talk is about how Google Chrome converts the code that we write into pixels on the screen. But you may ask, like, why? Why do we care? Why do we need to know any of these, right? Why do we need to know all these under-the-hood stuff? Why am I doing this talk? Basically, I've gathered 3 reasons for that. First of all, there are many best practices in the industry which some of us web developers follow kind of blindly without really knowing the reasonings behind them. So I'd like to clarify the motivations behind some of these best practices. And secondly, it's my own personal experience. Like, as I learn more and more about the internals of the browsers, I noticed that I was getting faster in debugging issues related to performance, layout, and all that stuff, and not just debugging. I noticed that the way I was authoring my web applications got significantly better as well. So I'm hoping that it will have the same effect on you guys as well. And last but not the least, the browsers are these amazing, advanced, black boxy tools that we have all based our careers on in one way or the other. Knowing how it all works under the hood is just freaking awesome, right? So before I start the journey, I would like to take a moment to peek into Chrome's architecture from 10,000 feet, just so that we get to know the major components in Chrome, all right? So there is, first of all, one and only one browser process. And it's responsible for the UI of the browser, the things like the tab strip, the navigation buttons, the address bar, and all that, right? And the browser process creates a bunch of threads, like the UI thread, the network thread, and the storage thread. And then there is the renderer process. For every tab that you open, the browser process creates a new instance of the renderer process. And the responsibility of the renderer process is to render the content of the page. Which is why Blink, the rendering engine of Chrome, and V8, the JavaScript engine of Chrome, they exist within the renderer process. And the renderer process also creates a bunch of threads, like the main thread. This is where Blink runs, the Compositor Thread, and the Raster threads, and we'll get into the details of all of these in just a little bit. Another thing about the renderer process is that it is actually sandbox. It cannot go make network calls directly. It cannot go make file system calls directly. It has to go through the browser process in order to do that, which justifies the existence of the network thread and the storage thread within the browser process, right? And all these communications between the browser process and the renderer processes happen via Chromium's inter-process communication channels. The true responsibility of making graphics layer commands to put pixels on the screen, that lies in a separate process called the GPU process, and it has one thread, the GPU thread. Now that we are kind of used to have a high-level overview on Chrome's architecture, we can start the journey, and the journey starts with the user typing in the URL in the address bar. The first thing that Chrome does in response to this is to figure out the IP address for this domain name in a process called the DNS resolution. And it works like this. The network thread within the browser process is first going to check Chrome's own internal DNS cache to see if the IP address has already been resolved. If it's not in there, Chrome's going to ask the operating system. If it's not with the OS is going to talk to your router. If it's not with the router is going to reach out to your ISP, the internet service provider. If it's not with the ISP is going to make a recursive query through different layers of name servers until the IP address is resolved and it makes its way back home to Chrome. Now, Chrome has the IP address of the server that it needs to connect to. So it does just that in a process called the TCP connection. So if DNS resolution is like finding out the phone number of the person you want to call, establishing a TCP connection is like actually making that call, right? And just like when you make a call, you start off the conversation by saying hello to each other. Chrome and the server, they're going to do the exact same thing. They're going to say hello to each other in a process we call TCP Handshake. And it works like this. Chrome's going to send a packet to the server, SYN packet, hey, server, let's synchronize. Server is going to respond to that by sending an ACK packet, the acknowledgement. Chrome's going to send an acknowledgement to that acknowledgement. This is Chrome and the server saying hello to each other. Now that the connection is established, Chrome's going to send the actual request to get the content. Server's going to handle that request and generate some content, like index.html, for example. Let's say that content is about 45 kilobytes large. The server is not going to send back the entire 45 kilobytes at once. It's only going to send back 14 kilobytes. Why? Because TCP, the protocol, is built this way. See, TCP does not know how big a bandwidth there is between the server and the client. So to figure that out, it starts off small by sending a small amount of data. Why 14? Because each TCP segment has a payload size of 460 bytes, and TCP starts off by sending 10 TCP segments. Once the server receives the acknowledgement for the 10 TCP segments, it's going to double that amount and send 20 TCP segments back to the browser. And this process goes on until either a certain limit is reached or until all the content is delivered to the browser. Now, the important takeaway here is TCP starts slow. No matter if you're on HTTP 1 or HTTP 2, no matter what kind of generous bandwidth you have got going on at your home, TCP is always going to cap that first server round trip to 14 kilobytes, which is why you may have seen the best practice running around in the industry to put that critical content within the 14 kilobyte threshold. That's the reason behind that magical number 14. Better yet, put that critical CSS, the above the fold CSS, right? The CSS that we need to deliver to the browser as soon as possible. Inline that within the 14 kilobytes so that the browser has everything that it needs to render content in the first server round trip. This is the fastest we can render. The only way to render faster would be to get the servers physically closer to the browser. See, TCP is a paranoid protocol, right? So there's a running joke in the industry, like if there are two people who are saying a joke to each other, using TCP as the protocol, their conversation would go kind of like this. Hi, I would like to hear a TCP joke. Hello, would you like to hear a TCP joke? Yes, I would like to hear a TCP joke. OK, I'll tell you a TCP joke. OK, I'll hear a TCP joke. Are you ready to hear a TCP joke? Yes, I'm ready. See, it goes on and on because TCP is a very paranoid protocol. It's built to serve data reliably over a highly unreliable channel, which is why it needs to do this back and forth, get confirmation like, hey, did you get the data? I'm about to send you data. So there's a lot of back and forth involved. There's a lot of server round trips involved, which is why it's important to know that if you want to deliver fast, you need to target for that first server round trip by aiming for that 14 kilobyte marks, right? So there's a lot going on in the network stack, like, for example, setting up HTTPS connection is another thing, but I'm going to skip all of those to keep the focus on the rendering side of things, right? So let's say the server starts streaming HTML to Chrome. The network thread in the browser process is going to be the first one to get that raw bytes of HTML. So the browser process is going to create a new instance of the renderer process and ask it to render the page. And it's going to send all those raw bytes of HTML to the main thread within the renderer process, which is where Blink is running. Now we enter the Blink territory. This is where the real rendering happens. And the first stage of that pipeline is to parse the HTML. All these raw bytes of HTML, they are converted into characters based on the character encoding specified in the response headers. And those characters are used to create tokens. And those tokens are used to create C++ objects in the browser land that represents each and every tag within the HTML document. And just like those HTML tags are arranged in a hierarchical structure in the document, these trees, C++ objects, are arranged in a tree-like structure, which we call the DOM tree. See, the thing about this HTML parsing and creating of this DOM tree is that JavaScript actually blocks parsing this HTML. Say you have a script tag like this in the head of your document, right? Chrome is going to parse the HTML, and then it sees this external script, and it's going to be like, oh, OK, hold on. I need to download that script first. I'm going to pause the parsing. I'm going to download that script, parse it, execute it. Then I'm going to continue with parsing the rest of the HTML, right? See, JavaScript is usually there in the page to add some interactivity to a page full of content. It should not be blocking the rendering of that content, right? Which is why there is a best practice in the industry to put these scripts at the bottom of the document. Because when you do so, Chrome is going to parse the entire HTML, render it, and then it's going to do the JavaScript work and put those interactivity into the page, right? There are better ways to load scripts nowadays. For example, you can use the async attribute. If you use an async attribute, those async scripts are going to be downloaded parallel to the parsing of the HTML. Do watch out, though, because Chrome is not going to respect the order in which the async scripts appear in the document. If there are order dependencies, it's basically first come, first execute, right? So if there are order dependencies between the scripts in your page, you ought to use the defer attribute. Because if you use defer attribute, the deferred scripts, just like the async scripts, are downloaded parallel to the parsing of the HTML. But Chrome is going to respect the order in which deferred scripts appear in the document. Chrome also does this new thing nowadays. So if your JavaScript is like greater than 30 kilobytes large, it's going to parse it on a separate thread. And that's great for performance for two reasons. Number one, the parsing happens parallel to the download. So your parsing of the script is going to finish right after the download. Second, it's going to bring a lot of activity out of the main thread. Main thread is a performance-sensitive area. There's a lot going on in there already. Anything that comes out of it is going to be better for performance. So Chrome helps us with this. In the same way, CSS is called render blocking. If you have an external style sheet like this in your document, Chrome is going to parse and render the content until it sees this external style sheet. Then it's going to be like, oh, I'm going to pause the rendering. I'm going to download that CSS first, and then I'm going to render the rest of the content, which is why there is a best practice in the industry to put this CSS at the top of the document. So we ship all the information that Chrome needs to render the page as soon as possible. Better yet, like we saw before, put that in critical CSS in that initial 14 kilobyte mark so that we do not even incur that additional HTTP request. We get that as soon as possible. And then load the rest of the CSS async. What does it mean to load CSS async? It means to load the style sheet in a way that browsers don't block rendering while they're downloading the style sheet. Unfortunately, we do not have an async attribute that we can simply put in the link tag. We do, however, have a nice workaround, and it works like this. So you basically put a style sheet in the same way as we do regular style sheet, but you set the media to something else than the current media. So if you're creating an application for screen, you set it to the print. When browser sees this, it's like, oh, it's for something else. So I'm not going to block the rendering on this style sheet. But we do want the styles to be applied to the current document, right? So in order to do that, when the onload happens, we're going to set the media back to all so that the styles get applied to the document. This is the simplest and the most cross-browser way to load CSS asynchronously right now. All right, after the HTML is parsed and then the DOM tree is created, the next step in the pipeline is to figure out how each node in the DOM tree is going to look like in a process called Recalculate Style. In order to do that, Chrome is going to use the style information that we provided and its own internal default user agent style sheet, and it's going to traverse this DOM tree, computing style for each of the node. And computed style is basically a giant map of all the CSS properties that are out there and their corresponding values. And this is calculated for each of the node. Now we know how each node is going to look like. The next step in the pipeline is to figure out where they're going to end up relative to one another in the screen, in a process we call layout. In order to do that, Chrome is going to create a separate tree from the DOM tree called the layout tree. And the layout tree only contains the DOM nodes that are going to be visible in the document. Notice how the head tag and the meta tag are no longer present in the layout tree, right? In the same way, if you had display none some of these elements, they would not appear in the layout tree either. After constructing the layout tree, Chrome is going to traverse through the layout tree and figure out geometry data for each of the node in the layout tree. Geometry data are things like the x and the y coordinates in the viewport, and width and height and all that stuff, right? Now we know, after doing the layout, we know how each node is going to look like and where they're going to end up in the viewport. So we can go ahead and paint them. Painting happens in two stages. In the first stage, we're just going to collect the paint operations, the command that we need to execute later to actually create the image. For example, for HTML, we would have to draw a rectangle. For body, we'd have to draw another rectangle. For paragraph, we have to draw a text blob. For span, another. It's kind of like the Canvas API that we're used to, right? The execution of all these paint operations to create the image happens in a separate process called rasterization. And when these commands are executed, we actually create image. That image is uploaded to GPU memory as texture. But like I said before, render process or sandbox, they cannot make GL commands directly. So those commands are actually proxied through the GPU process. And now we have the code that we wrote as pixels in the GPU memory. It's not on the screen yet. Let's do a quick pipeline recap. We started by parsing the HTML into DOM tree. Then we figured out how each node in the DOM tree is going to look like in a process called Recalculate Style. Then we figured out where each node would end up in the viewport in a process called Layout, and we constructed a layout tree for that. Then we collected Pane operations for the layout tree, and then we executed those Pane operations in a process called Rasterization, and then we uploaded the generated image to GPU via the GPU process, therefore having the code that we write as pixels in the GPU memory. But things are not as simple as that. They do get complicated. See, Chrome does not get to run this pipeline once and call it a day because things change in the page. And things can change because user may scroll the page, user may pinch to zoom, there may be some animations happening, or JavaScript may be changing the state of things in the page, right? See, if Chrome was to run this pipeline every time something changed in the page, then we would easily blow out the frame budget. What is the frame budget? So most of the screens that we have right now, they have the refresh rate of 60 Hertz, meaning the screen refreshes 60 times per second, meaning the operating system is going to talk to Chrome and ask it to ship a new image, ship a new frame 60 times per second. So if the user is scrolling the page, to represent that scroll movement, Chrome has to create 60 different images every second. That's a lot of work to do. If we zoom in to generate every single frame, Chrome has basically only 16 milliseconds, right? So if Chrome was doing the entire rendering pipeline for every single frame, and if one of these pipeline stages takes just a little long, then we would miss the frame. And this is what the users would perceive as a stutter in the movement, which is what we call jank. Mind you, all of these things are happening in the same main thread where JavaScript is also running. And JavaScript is a highly performance-sensitive area and can make us easily blow out a couple of frames. And it only requires a couple of missed frames for users to perceive the jank. So in order to prevent this, in order to prevent the main thread from becoming the bottleneck in rendering, Chrome works with this concept of layers and compositing. So what are layers and compositing? Say you have a page like this, and there are a couple of elements in there, and they animate on top of each other, like this, right? So if Chrome was creating only one image per frame, to represent this animation, these moving elements, Chrome has to recalculate their style, do the layout, do the paint operations, every single frame, right? So Chrome has to run the entire rendering subsystem for every single frame, and there's a lot of work to be done in performance-sensitive area like animation, right? So in order to do this efficiently, Chrome splits the page into separate layers, and each layer gets uploaded to the GPU as a separate image. So now Chrome, instead of doing all this work on the main thread on the CPU side, is just going to talk to the GPU like, hey, GPU, you already have those layers as images. Just run these commands so that they look like they're animating. Do it on your side. Chrome doesn't have to do anything on the main thread. Nothing happens on the CPU, right? So that's the way the fact that the page is split into different images, those are layers, and the fact that the commands are generated to put them all together into one final image of the page, that's composition. So let's see how layers and composition actually work. Remember the layout tree? So that was the tree where we knew how each node is going to look like and where each node would end up in the viewport, right? Chrome is going to create a new tree based off of layout tree called the layer tree. And by default, the root of the document automatically belongs to a layer. So HTML and all its children belongs to one layer automatically. But using CSS properties like will change transform or 3D transformations, you can bring out an element and all its children into a separate layer. Now Chrome, instead of collecting paint operations for a layout tree, it's going to collect paint operations for each layer. This layer tree and the paint operations, that's all we need to be able to ship a frame in Chrome. So what Chrome does is the main thread is going to hand off all this data, the layer tree and the paint operations, to a separate thread called the Compositor Thread. From this point on, Compositor Thread is capable of rendering a frame of the page without consulting the main thread, right? And Compositor Thread is also the one that's going to execute these paint operations to create bitmaps. And it can do this parallel. So if you have multiple layers, it can rasterize content by creating multiple raster threads, and it's going to raster those images using multiple threads. some layers are really large, right? And they may go beyond the viewport. And the user may never even see that part of the layer. So it would be kind of wasteful for CPU and memory if Chrome was rasterizing the entire layer and the user will never see that, right? So in order to be a bit more economical about that, Chrome is going to, the compositor thread is going to chunk large layers into smaller tiles. And the compositor thread is only going to raster the tiles that are in the viewport or are very close to the viewport, right? After this, we have the images generated for each of the layers. So compositor thread is going to generate GL commands to composite these different layers together into one single frame, which we call the compositor frame, and it's going to hand that information to the browser process. And the browser process is going to do its own composition. It's going to add this UI frame, the browser UI, around the compositor frame, and it's going to talk to the GPU process and issue the draw calls to put the pixels on the screen. Now we have the code that we wrote as pixels on the screen. There's a lot that happened here, so it deserves another pipeline recap, right? So let's go ahead and do that. The timeline is going to look a little bit different. We now have the renderer process where we have the compositor thread, the rasterizer thread, the main thread. Then we have the browser process with the main thread, and then we have the GPU process. So let's look into how this timeline looks like when the page is loaded initially, during the initial render. We're going to start off in the main thread by parsing the HTML to create the DOM tree. Then we're going to figure out how each node in the DOM tree is going to look like in a process called Recalculate Style. Then we're going to figure out where they're going to end up in the viewport in a process called Layout. Then we're going to create multiple layers based off the layout tree. And then we're going to collect paint operations for each of the layers. And we're going to hand off all that information to a separate thread called a compositor thread in a process called commit. Compositor is going to chunk large layers into smaller tiles, and it's going to use the raster thread to rasterize those paint operations into bitmaps. And then the compositor thread generates GL commands, the graphics layer commands, to put these different layers as one final image of the page called a compositor frame, and gives that information to the browser process. The browser process is going to add its own UI-related stuff around the compositor frame, and is going to issue the graphics call via the GPU process to put the pixels on the screen. So this is everything that happens, the rendering pipeline that kicks off when we load the page initially. What happens when the page gets updated because of JavaScript? So let's look into the pipeline when that happens. See, one thing to know is a lot happens in the main thread, but compositor thread is really the boss. And as the boss, compositor thread is the one that receives all the input events. They are proxied through compositor thread before the input events reach the main thread, so that compositor thread gets the first crack at handling those input events. And if compositor thread is not able to handle the input events, it's going to forward those events to the main thread. This is where JavaScript comes in. This is where the code that we write come in, right? So JavaScript is going to handle the input events. And JavaScript may do things like requestAnimationFrame. We may change the DOM in a certain way, add classes, remove classes, whatever. Whenever we dirty the DOM, the main thread is going to send a signal to the compositor thread like, hey, we changed something on our side, so let me know when I need to create a new frame. Compositor thread, being the boss, is also the one who is synchronized with the refresh rate of the browser, which we call vsync. So next time the operating system is going to ask compositor thread to create a new frame, it's going to start the process to generate a frame and let the main thread know about it. And on the main thread side, we're going to kick off the rendering pipeline to create the frame. And it starts off by executing the requestAnimationFrame callbacks. And then, based on the changes we did, it's going to hit the rendering pipeline, which you've already seen multiple times today, the Recalculate Style layout, layers, and paint operations. The important thing to notice here is the requestAnimationFrame callback is the one that gets called as close to the screen refresh rate as possible. And not only that, it gets called right before Chrome's rendering pipeline starts. So if you're animating things, if you're changing things in the DOM, this is the best place to do so because it happens right before the rendering pipeline of Chrome. And now, after we collect the paint operations, the same story again, we're going to hand that information off to the compositor thread. Compositor thread is going to prepare tiles, schedule rasterization, use the raster threads to do the rasterization, generate the compositor frame, give that off to the browser process. Browser process does its thing, and it's going to make the GPU calls to put the pixels on the screen. Now you may ask, like, what's the advantage of this compositor thread? When do we really see the benefits of it? Why is this architected like this? We will see the benefits of the architecture like this when things are, for example, scrolling or when animations are happening in Chrome. For example, oh, by the way, I missed this part. So after doing all this work, if there is still some time left before the next vsync happens, like, so the main thread is like, oh, I got nothing else to do, that's when the requestIdleCallback gets invoked. So if you have non-essential work that needs to be done in JavaScript and it does not touch the rendering pipeline, requestIdleCallback is the best place to do. Think stuff like analytics or something like that, right? So let's look into this timeline when scroll happens. Then we can really see the benefit of the composited architecture. So when user is scrolling the page, the compositor thread is going to be the first one to receive the scroll events. And the compositor thread already has the paint operations and the layer tree. So what it does is basically going to rasterize the new stuff that is coming into the viewport, if necessary. And then it's just going to talk directly to the GPU, like, hey, GPU, just move this page by the amount of pixels that the user scrolled the page. Just translate it. So it's going to go straight to the GPU. It's never going to come to the main thread. So your main thread can be completely hogged up in JavaScript. Like maybe there is some execution happening because a SHR request got completed. Maybe the timer got fired. Anything can be happening on the main thread, but it does not matter. The scrolling is going to be happening as smooth as it can because of this architecture. But watch out, though. We may write some code that can actually destroy this. So yeah, Chrome can scroll content smoothly even when the main thread is busy. That's what we saw. But if we write code like this, if we attach an event listener to the touch event, JavaScript can actually cancel that touch event. And if that happens, Chrome has to cancel the scroll as well. So if we write code like this, basically the compositor is going to be like, oh, the main thread may actually block the scroll. So let me talk to main thread first. And it's going to ask main thread, so I see you have some JavaScript that may block the scrolling. Are you going to do that? And then main thread is going to execute the JavaScript. It's like, oh, no, we didn't block any scrolling. And only then the compositor thread can do its own scroll. So we basically brought the scrolling back into the slow main thread. That's not what we want to do, right? So in order to prevent that, we need to use this thing called passive event listeners. And you do that by sending a third argument to the add event listener function, which is passive true. When you do this, you're basically telling Chrome, like, you know what? I'm attaching event listener for the touch event, but even though I'm doing this, I promise that I won't cancel the scroll event, cancel the touch event, so you can go ahead and do the scroll on the compositor side. And Chrome continues to do the fast scroll only on the compositor, never coming to the main thread. All right? In the same way, animation, when things are moving on the screen, the compositor thread is going to be the one who is first notified that, hey, we need to create a new frame. And the compositor doesn't even need to go back to the main thread to do the animation. It's just going to apply new transformations and just talk to the GPU directly, never coming to the main thread. So your main thread, again, can be completely hogged up in JavaScript. Still won't matter. Your animations is going to run completely hitch-free. But watch out. All the elements that are animating on the screen, for them to be done on the compositor side, for them to be GPU accelerated, they need to exist on a layer of their own. And we already saw how we can do this by using will change transform. That works. Or by using 3D transformation. We saw that, right? But that's not enough, actually. Only 4 CSS properties are actually can be animated on the compositor side. And those are opacity, scale, rotation, translations. Any other animation needs to come back to Blink, come back to main thread. So try to keep your animations in one of these 4 properties. And there are tricks to do that. If you're animating height and width, try to animate scale instead. If you're blurring the image, and you have that blur animation, maybe you can already create the blurred version of the image and then animate the opacity. That does the same thing. And if you're animating the top and left positions, maybe you can animate 3D translations instead. So there are tricks to put your animations within these 4 CSS properties, right? All right. Again, watch out, though, because all these different layers, they're uploaded to the GPU memory as textures, and that takes up memory. A lot of memory. So if you're on a resource-constrained device, then you can really choke the graphics memory with all these layers. So don't go about creating layers for every single element that are out there in the page. You're going to have a hard time in resource-constrained device. So use the layers with caution. All right? Actually, that's all I have, what I wanted to share with you guys regarding the Chrome's rendering pipeline. So there's a lot that happened. So I want to nail all these ideas down by showing some demo, right? So let's go to the demo. What I'm going to do is I'm going to actually use Chrome DevTools to visualize all this information that we saw. So that, because then you can really go home and do it yourself and check it out yourself and see all these rendering pipeline happening and DevTools telling you how they happen. So I've got a page over here. It's a simple page, and I have a script which loads, and it's a slow loading script. So it takes 1 second to load that script. So we're going to first see the parser blocking behavior of JavaScript, how it shows up in DevTools. So I'm going to initiate the DevTools. I'm going to go to the performance panel, and I'm going to make a recording, and I'm going to go to that page. And when that page is loaded, I'm going to stop, and there we get, this is what we call the flame graph. This is where all this information, crazy stuff about Chrome's internals is happening. So let's look into this. I'm going to start off on the network tab up top here, right? So we started by downloading the HTML. So I'm going to zoom in here, and then I'm going to see everything is clear, visible. By the way, OK, cool. So we are going to download the HTML, right? And here we started getting the first byte of HTML. Then it gets downloaded. And if I hit the shift, then I can see this pointer as well that gives us a nice indication of where we are in the flame graph. And I can go down here and zoom in. And then we're going to see, OK, when the download of the HTML completed, we're going to start parsing the HTML. Then I'm going to go down to the summary tab here. And if you see, we only parsed from line 0 to line 3. That's where the script is. This is the parser blocking behavior of external JavaScript, right? So when that script gets downloaded, which is a long one, and you can see that up top here, when that script gets downloaded, let's see, it gets finished over here. I'm going to go down here, and then we're going to see that we're going to parse the rest of the HTML here, right? So if I click on this and look into the summary again, we went from line 4 till -1, which means we parsed the rest of the document. This is the parser blocking behavior that I talked about of JavaScript. Not only that, if you look into, if you go to the flame graph at the time when the script was downloading, and if you look into the frames that Chrome was shipping, you will see we were showing the content from the previous page, right? So we were not only blocking the parsing, because the parsing was blocked, the rendering was blocked as well. We were just showing the old page. And only after the script got downloaded over here, we showed the new content, right? Which is why we need to load scripts differently. And we learned that you can use Async Script. So let's see how Async Script changes this timeline. So I'm going to go ahead and put the async in here in the script. And I'm going to go back, clear this, and then start recording again, and go back to the page again. When it's loaded, let's stop. Now let's do the same thing. Let's go to the network tab up here. And looks like the HTML has stopped downloading here. So I'm going to zoom in here, and I'm going to see that we are started parsing the HTML. If I click on this one, I see that we parse pretty much the entire document, right? So this is why, let me go back. So this shows us that if we use async scripts, the parsing of the HTML is not blocked, and the download of the script happens over here, parallel to the parsing of the HTML. And when that script is downloaded, that gets finished here, we're going to evaluate and compile and execute that script, right? So that's why it's important to use the async scripts. In the same way, I would also like to show you guys the threaded parsing of Chrome that I talked about. Unfortunately, I couldn't see that in the latest version of Chrome, but I do have saved a profile from before, like last week. So I'm just going to go show you guys that. So what I basically do is I load a big chunky library, like Moment.js is pretty chunky, right? And I want to show you guys how Chrome parses the script on a separate thread. So I have that profile saved somewhere. So I'm just going to load that up, threaded parsing. And when that loads up, I'm going to zoom in over here. Moment.js is downloaded. It's evaluated here. But you can see down here, there's a separate thread that is parsing the Moment.js, right? If your script is larger than 30 kilobytes, Chrome is going to do this for performance. So parsing happens parallel to the download, and when parsing finishes, we're going to go back to the main thread to evaluate and execute the script, right? So this is Chrome helping us for performance. Actually, this is the way that Facebook, despite shipping a ton of JavaScript to the client side, does a lot of work out of the main thread. All right, so that's the first demo. The next demo that I would like to show you guys is the timeline within the DevTools when the page is loaded initially. Everything we learned, how that appears within the DevTools, all right? So in order to do that, I have a simple page. It just says, hello world, nothing complicated. So I'm just gonna basically start profiling and reload the page. Hit that button. It's gonna reload the page, and it's gonna create the profile as well. There we go. So let's see what happens. So our HTML is over here, right? That gets downloaded over here, and we're going to start parsing the HTML here. And then, as a result of parsing the HTML, what do we get? We get the DOM tree. Then we're going to figure out how each node in the DOM tree is going to look like in a process called Recalculate Style. Then we're going to figure out how each node is going to look like in the viewport in a process called Layout. Then we're going to create layer tree from the layout tree, create separate layers for the page, and then we're going to collect the Pane operations for each of these layers. And like I said before, the Pane operations is basically recording the commands only, not actually executing it. And you can see that if you click on the Pane, where is that? Okay, so in this case, it didn't record it, but you could see in the DevTools, there's also a place down here in the summary called Pane Profiler, and you can really see the commands that DevTools actually captures for each of these Pane operations as well. But once the Pane operations are captured, then we're going to give all that data to a separate thread called the Compositor Thread in a process we call commit, right? In DevTools, you see that as composite layers. It's a little bit badly named. Composite layers is basically committing all this data from the main thread to the Compositor Thread. It should be called commit layers, but unfortunately, it's called composite layers, and it's doing the same thing. And then it's going to come down to the Compositor Thread, and Compositor Thread is the one that's going to raster execute those Pane operations to create bitmaps using multiple raster threads that you can see over here. The raster thread is going to do its job, you can see over here, and then eventually the raster thread is going to use the GPU process, which you can see down here, to put the pixels on the screen. Let me quickly see if we can see the Pane operations. Unfortunately, it's not here. Anyway. All right, so that's the pipeline, that's the timeline that we can visualize all this information using Chrome DevTools for the initial render of the page. Now let's look into how this timeline looks like when things happen because of JavaScript, right? So in order to do that, I have a simple page over here. When I click on it, this thing starts animating, right? So simple. So let's go ahead. I'm going to start capturing, then I'm going to click on it, and then stop the capture. So immediately you can see there's a lot going on in the main thread here. So let's zoom in. So if I go in here, mind you, this is the main thread, right? I'm going to see that we are handling the click event. That's right here, right? As a result of the click event, we are collecting. We're doing something that may change the state of the page. We're animating this element, right? So I told you before that when that happens, the main thread is going to send a signal to the compositor thread like, hey, compositor, I changed something. So let me know when I need to start creating a frame. So compositor thread is down here. You can see that compositor thread receives this event called needs begin frame changed. So compositor thread is notified that frame needs to be generated. So let the main thread know about that. Later, when vsync interval happens, compositor thread is going to start generating that frame. And over here, you will see it's going to request the main thread to create a new frame. That's going to come back up here as frame start on the main thread. So main thread needs to start generating the frame, right? And like we discussed before, it's going to start that process by executing all the requestAnimationFrame callbacks. That's exactly what we see here, right? And as a result of that, it's going to hit the rendering pipeline like recalculate style, layout, creating a layer tree, pane, composite layers, and all that. So this is what happens, and it goes all the way back to the GPU, but I don't need to repeat that because we've seen this process before. So this is how the timeline looks like when things are changing because of JavaScript. That's what the Chrome DevTools give us. Now, we immediately notice that there's a lot going on in the main thread over here when this animation is happening, right? So when things are animating, we want main thread to be not involved at all. As much as possible, less involved, but hopefully not involved at all. So let's see if we can figure out what the problem is and optimize that. If we zoom in a little bit, like for each frame, so this is a frame, this is a frame, this is a frame, right? For each frame, we are basically hitting recalculate style, layout, creating a layer tree, paint operations, composite, everything is being done. So we need to optimize that. There's another way to view this kind of performance bottlenecks in DevTools. You can hit Command-Shift-B in Mac to bring out this command menu, and then you can type in some commands like performance monitor. What this does is it brings up this nice panel that gives you real-time update about the health of your application. Here, I can check in layouts. I want to see how many layouts are happening. I want to see how many style recalcs are happening. And then Chrome's going to give us this real-time update over here about all the things that is happening for this frame, right? And I can see that we are smack in the middle between 40 and 60. Now, that information is actually here as well. We are doing 60 recalculate style every second and 60 layouts every second. That's bad. We ought to improve that. Another way to visualize this, visualize the paint work, is again back to the command palette, Command-Shift-P, and type in show paint flashing rectangles. When you do this, every time Chrome is painting something, it's going to show us with this giant flashing green box. This shows us that for this animation, we are basically painting every frame. So there's room for improvement there, right? Another thing that we learned today, I'm going to hide that rectangle. Another thing that we learned today was in order for the animation to be done on the compositor side, we need to put that moving element in a layer of its own, right? And we learned that we can do that by using something like will change transform. Right? So let's go ahead and try that. I'm going to do that. I'm going to reload the page. But how do I know if this element is on a separate layer or not? Again, back to the command palette. So I'm going to hit Command-Shift-P and do show layer borders. All right? And then what it's going to do is for every element that exists on a layer of its own, Chrome is going to surround that element with this orange border. Right? And up here, you also see this like cyan-colored border up here. And those are the tiles. If there are large layers, then Chrome is going to chunk it into smaller tiles, right? Those are the tiles, and the orange one is the layer border. So we now can confirm that this element is existing on a layer of its own. There's another way to visualize this as well, and that's using the Layers panel. So if you hit, again, surprise, surprise, Command-Shift-P, and do Show Layers, let me just show layers, then we get this Layers panel, and here you can visualize in 3D view all the layers that are existing in your page. Yeah? So you can, not only that, there's some useful information in here. You will see why each of the element got promoted into a layer of its own as well. For example, in case of this paragraph, we use will change, right? So the compositing reason is will change transform. Not only that, it will also show you how big that is going to be in the GPU memory. It's going to be big. It's going to be 1.3 megabytes just for that text, right? So that's why I mentioned earlier, watch out for these layers. If you create a lot of layers, it's going to take up all the memory. So layers panel is a nice one. So it shows you this animating view as well. It may crash my DevTools, but OK, it's not crashing this time. All right, I'm going to close this off. So now we know that this element exists on a layer of its own, right? By the way, I also created this button here to see like if the animation is happening on the main thread, and if I hog the main thread, then that animation should be affected, right? So we now put this element on a layer of its own. So does that mean that it's animating on the compositor side without coming to the main thread? Let's check. Let's run the animation. I'm going to hit the hog main thread button. It's basically a while loop for a while. And then hog it, and then the main thread got hogged because the active state of the button is stuck, right? And the animation is completely stuck as well. So we're still doing stuff on the main thread. So we need to do that better as well. We learned another thing today, right? It's not just enough to put elements on the layer of its own. We need to use only 4 of the CSS properties: rotation, opacity, translations, and scale, right? So over here in the code, I'm animating left, CSS left property. Instead of doing that, let's go ahead and animate the 3D translations. Change that code. No more animating the left position. And then go back over here. I'm going to let the animation happen. I'm going to hog the main thread again. Animation continues, right? So this is the benefit of the compositor thread. That's how you do your animations out of the main thread, right? And this is basically the purpose of my talk as well, right? Having all this knowledge about the inner working of the browser, you don't need to go into like deep details, but having the general overview is going to make all this information that comes out of things like DevTools a lot more digestible, because I've seen a lot of developers who go into the DevTools and flame graph and see like, oh my God, that's a lot of data, and they just give up on that, right? So my purpose of this talk is to make those data a bit more digestible, right? And then when all those data from the tools are digestible, you can use those tools to the fullest. You can take advantage of those. So that's basically the purpose of my talk, and that's the entire thing that I wanted to show you guys today, including the demo. So let me quickly go back to the slides. This slide is available in this link, so bit.ly code-2-pixels. And see, I'm not a guy who works in Google, so I don't have contacts with all these amazing people who work behind these awesome tools. And I'm not a C++ developer either, so I wouldn't take the hard way of going into the Blink source code, although I did try that and I quickly gave up. So this talk is basically the result of my own experiments and lots and lots of research that is all available on the internet. So I've collected all these research materials and put it in this link. Code to Pixels learning material. So you guys can go ahead, go home, and if I have sparked the interest in you, you can check out these learning materials, and hopefully you guys will go much farther than I have. And also another reason that I give this talk is, actually, I do a lot of talk on performance stuff, but talking is easy, right? I needed to back that up with some result as well. And I really like this iOS App Store. This is the animation that happens in the iOS App Store. It's so smooth. It's buttery smooth. The UX is great. I actually go to the iOS App Store not to download anything or update anything. I just go there to play with these animations. It's so beautiful. So I wanted to replicate this on the web. So I started this project called Web App Store, and I'm trying to recreate the iOS App Store using completely web technologies to prove that web is getting there, right? Using all this knowledge, we are able to achieve quite some nice stuff. So another purpose, kind of like a side purpose of this talk, is hopefully I've sparked that interest in you guys. Hopefully you guys will go home and read more up on it. And maybe some of you will come help me in this project, because I definitely need some helping hands and some motivation as well. But that's not the point of the talk. The point of the talk is web is powerful. It's getting more and more powerful every single day. So keep making those beautiful stuff that you are making on the web. And thank you very much for listening.
All right. Thank you so much, Prashant. Well done. Would you like to join me for the conversation?
Yeah, sure.
Well, so questions. I have many questions, but I actually want to ask
I thought I was done.
Yeah, so it's interesting because in the past we've been thinking about 30 frames per second, we moved to 60 frames per second, and now there are discussions about 120 frames per second. And that, of course, reduces the budget again, twice making it almost impossible to do fancy things like parallax and changing backgrounds and all of that. So what would you recommend to do to people who are dealing with really intense animations or really intense, this kind of really complicated movements, maybe data visualization, things like that?
Yeah.
There's also WebAssembly we could use, right? Is there so we're talking about rendering, but are there any other improvements you can do beyond that?
Yeah, for sure. So 120 hertz is definitely going to bring up challenge, because our budget is going to get significantly lower. And there's going to be a limit sometime, right? For even with the 60 frames per second, you can hit that limit, because there is sort of an overhead between when the event comes into the operating system and when it gets relayed to the main thread of the browser. There is just this overhead that you cannot avoid, right? So it's never going to be super smooth, and then 120 hertz is going to change that game, and we even have lower budget. So if you are doing crazy animations, there are other technologies that are out there you can explore, like WebGL. We have several WebGL talks later today, right after this one. So I would say those technologies can be very interesting for you. You can talk directly to the GPU, work with the shaders, and do crazy stuff over there directly on the GPU. And those are probably going to get you that very needed performance if you're looking for that.
That makes sense. Ivan is wondering, why shouldn't we animate top left with will change top left rule? Isn't will change top left, will it not move a block to another layer so we can animate it smoothly? I mean, will change is a good way to go ahead there, right?
I'm not sure if I understood
so if you're using top left in CSS to move things or things like that, of course you can still use it by also using will change, or is it better to use
okay, gotcha. All right.
Slate 3D and all?
So it is still better to use translate 3D because will change is going to bring that animating layer and a layer of its own, but the top and the left animation needs to happen on the main thread. So Blink still needs to get involved. So if we want to animate the position of an element in the viewport, we need to use the 3D transformation so that we never come to the main thread. And if you want a clear picture of all the CSS properties and whether or not they will come to the main thread, I think Surma and Paul Lewis created this really nice website called CSS Triggers. CSStriggers.com, and you can see that what kind of effect each of the CSS properties will have in the rendering pipeline. And top left is probably going to touch the layout because you are changing the layout. You may push some other elements outside. So it will still come to the Blink area to do those things. So that's why you need 3D transformations. Although I have to mention that if you were using 3D transformation, that's enough to put an element on a separate layer of its own. So you will probably not need will change there.
Yeah,
a 3D transformation will be enough.
Oleg is he found the rendering talk nice, but he also wondering, are all these wonderful cool dev tools features available in mobile Chrome as well?
Remote debugging. If you're on mobile Chrome and you debug that thing remotely using ESP and inspect, you can go to Chrome inspect, and then you can see all the remote debugging instances that are available. You can do USB debugging as well. And then you can use your familiar Chrome dev tools for remote debugging as well. That's fantastic.
Okay. So when it comes to debugging, especially this kind of tough animations, or when you see that there is a jank, what would be your strategy to get there? Obviously, you go to the profiler and you go to the flame graph. What exactly are you looking for? Like, what are the warning signs that something is about to explode?
All right, so I start easier using Performance Monitor, for example, because that gives me like real-time information of what's happening, or flashing paint rectangles. That usually gives you puts you immediately into the right spot. But if you really need to know what's happening, then basically you want to create the timeline, and you want your timeline to be like super thin. Like anything that is becoming horizontally very big, that means that you have probably potentially a problem.
Which is also called long task, right?
Exactly. And Chrome is nowadays, DevTools is also indicating you about this long task. Like if you see that there are long tasks happening, basically JavaScript runs on the same thread where the rendering pipeline is running. So JavaScript is fighting with the UI thread of in the web world, right? So you don't want to hog that thread. Then the UI will freeze. And Chrome DevTools also indicates you with this tiny little red indicator in the flame graph if your JavaScript is taking too long. So I would look into things like those. I would try to see if the main thread is very busy, and I'll try to reduce that. Why is it busy? And all the other tools like paint flashing, layer borders, and these are complementary tools that help you figure that out.
Visualize and understand what's going on behind the scenes. Right. Another question that just came in. Isn't Z-index the same as using will change for layering? Which is preferable?
Z-index is more for the stacking context, to understand where elements are going to be relative to one another. Will change is Z-index, for example. If you use Z-index, it wouldn't bring that element into a separate layer. It would still be on the same layer, but it's just painted on top of that, right? So will change is doing this extra thing. It's going to bring that element into a separate layer, which we also call the compositor layer. So that's the difference between will change and the index.
It's been interesting because I saw the talk by, I think it was Eddie Osmani actually. He was speaking about all the things they did in V8.
The cost of JavaScript in 2019.
Yeah, I believe that. I was very impressed because they did a lot of things like script streaming, which they introduced recently. And essentially the things that you mentioned, if you have a big enough JavaScript, is going to be chunked, and then they start parsing right away. So it feels like browsers are trying almost desperately to help us as well. To get kind of faster. So what would be your strategy to deal with JavaScript altogether? Especially, you mentioned HTTP 2 and HTTP 1, and it was very nice to see this animation of how the handshake is happening and the 14 kilobyte and all that. Will not HTTP 3 change everything? I don't know if you're...
I heard about HTTP 3, but I'm still on HTTP 1, so I would not know about HTTP 3.
Yeah.
But again, in Addy's talk as well, the thing that came very clear to me is that right now, byte for byte, JavaScript is the most heaviest thing that we serve to the clients. Like images can be 100 kilobytes and JavaScript can be 100 kilobytes. Image, all you got to do is decode that image and you're done on the browser. While JavaScript needs to be parsed, compiled, and all this extra work needs to be done, right? So, so still, even though, like, I mean, I'm glad these technologies are there with HTTP2 server push and all that, but it's still the parsing of the JavaScript is going to be a problem. And also, emerging markets, like in India and stuff, like there are billions of people coming out using mobile phones every single day, more than ever before, and they are not on the fanciest phones in the market, right? They're on like really low-end phones. That means we are back into like several years back in terms of computing power. So JavaScript is going to be a challenging thing looking into my future, in my opinion.
Right, which is why it's also very interesting to see many, well, developers, I guess, starting looking into things like memory-aware components or network-aware components, where kind of based on your performance budgets, you will say, I'm going to target specifically 3G and 2G and 4G, and maybe for 3G I will, like slow 3G, I will turn off parallax. And I will turn off web fonts and other things. Those are a really nice, responsible way to program as well. But like I said before, I really like the fact that browsers are going out of the way to improve this stuff, and so are frameworks. Like one of the things that I heard with React Concurrent that got me really excited is that framework is going out of the way to take a category of these performance issues out of the developer hands, right? So now they have this like scheduling system, if I understand it correctly, that like if something component is being rendered and then another important task needs to be done, like handling user input, then React is able to pause that rendering and go serve the important stuff first. That's amazing. And I do believe that frameworks and browsers are the places where most of this like performance improvements should be done. Jan has sent 7 messages with the same question, so I better bring it up. Jan is asking, what about animation in JavaScript? So if you compare CSS animation and JavaScript animation, how would you deal with requestAnimationFrame, set timeout, and other things? Anything to keep in mind there?
I would try to, like, if JavaScript is involved, then main thread is involved. So there's no avoiding that. If you're responding to like touch events, then you're going to have to come to main thread, right? So that's out of the way. You can still try to keep your rendering pipeline as limited as possible, right? So instead of doing stuff that may change the, that may need, ask the browser to recalculate style, layout, and paint and all that, you may get off by just doing the paint part. Or something like you don't. Chrome does not have to hit the entire rendering subsystem, right? It can hit any one of those. So I would just watch out if we are doing animations in JavaScript. Just watch out that you're not hitting everything despite using JavaScript. And if you have crazy animation controls that's necessary, like pause, reverse, and all that, JavaScript is the way to go. Like so, yeah, that's how I feel.
But still, it's really kind of nice to see all this like code streaming and script streaming and code caching all coming in, and it seems like we're on a good track. And I'm really wondering how the interfaces will change if we at some point get to 120 frames per second. Being a, an expectation.
I was talking to the next speaker, Ivan. He is also very much into this stuff and super passionate about that. And I think he has some very nice opinions about 120 hertz. He has the Motorola Razr that is running on 120 hertz, and he's doing some crazy animations. He will be a good person to talk to as well.
He's also running a workshop tonight, by the way.
Oh, okay, I didn't know
really
that actually.
Well, worth going to.
That can be a very good follow-up talk on this talk, actually.
Wow. Well, I think the time is up, unfortunately. We can speak for hours, I'm sure. But, thank you so much for all the insights and demystifying the flame chart. And it doesn't look that scary anymore. It's not that flamey, is it?
It's not that flamey. It's actually flamier than you think it is.
Okay, so
I hope I got that message across.
Yeah, so when your colleagues pass by and you're in the flame chart, you're like, whatever.
He's legit. Like, it's like he's a genius. Like that's how you feel.
So, all right, thank you for being with us.
Thanks for having me.
Thank you.